Welcome. In this video, we're going to talk about derivatives. This is the first lecture out of two. We're going to go from the definition of what is a derivative to some rules to be able to calculate basically any derivative whatsoever. You will see that at the end of these two lectures, you will have a whole range of rules at your disposal. And in fact, on the quiz or on the exam, if you have to calculate a derivative, there will always be a way to apply the rules in an almost mechanical way. We're going to first talk about why we need to compute derivatives and how we define them. Then the bulk of the lecture is going to be devoted to derivatives of simple functions, and we'll finish off with a little bit about the so-called chain rule. Okay, so why are we interested in derivatives in the first place? In short, this is because derivatives allow us to compute tangent lines, or more precisely, the slope of a tangent line to a given curve. And let's go back maybe to when we looked first at limits. We introduced limits by saying if I have given an arbitrary curve, the graph of a function, then I can compute the slope of the tangent line at a given point by computing a certain limit. And that limit here is listed on the slide one more time. So basically what we did is we took a point on the parabola with coordinates x and x squared plus 1. And then we computed the slope of the line through that point and the fixed point P, where we want to compute the tangent line 2. And then we took the limit as Q goes towards the point P. And we found that in the limit, that slope of the tangent line is equal to 2. Now, if we have an arbitrary curve f of x, y is equal to f of x, then we can do the same thing. If we have a point here with coordinates a, f of a, so the point P, then we can compute the tangent line by taking another point Q with coordinates x, f of x. We compute the slope of the line through those 2 points, P and Q, and then we let Q go ever closer to P. So we'll take a limit as x goes to a. That limit that you get, and let's take with this slide for a little bit longer, then first of all, we have that the slope of the line through P and Q is given by what? Well, we have to take the derivative, we have to take the difference of the y coordinates, so f of x minus f of a, and then we divide by the difference of the x coordinates, so x minus a. That is the slope of the line through P and Q, and now we're gonna let Q go to P, so that is equivalent to taking a limit as x goes to a of that expression f of x minus f of a divided by x minus a. And this is a very special expression. This limit we're going to see coming up over and over again. We're going to give it a special name. This is what we're going to call the derivative of the function f prime evaluated at the point a, and it's given by this limit. If you look at, so we have that a little bit more nicely written out here on the next slide. We're going to say the derivative of f of x at x is equal to a is given by f prime of a, and that is defined as the limit as x goes to a of f of x minus f of a divided by x minus a, if the limit exists, of course. We will often say that the derivative, or we will refer to the derivative as f prime, note the prime sign. Now, we can rewrite the definition of the derivative in a slightly different way. We'll put h equal to x minus a, and if x goes to a, that's the same thing as h going to 0. So here we can write our derivative or our limit as limit of h, as h goes to 0, of what? Of f of x minus f of a. So if h is x minus a, then x is a plus h. So f of x becomes f of a plus h minus f of a. That's what you have here on top. And then you divide by x minus a, so you divide by h. That definition is completely equivalent as the one that we've seen before, but sometimes it is easier to compute. One more piece of terminology. If the derivative f prime of a exists, then we're going to say that f of x is differentiable at x is equal to a. Now let's compute our first derivative. So here you have a function 3x squared plus 7x minus 5, and you're asked to compute the derivative at x is equal to 1. At the end of this lecture, we will do this in one step. But for now, we have at our disposal is the limit definition, so let's use that to compute our derivative. So we have f prime of 1 is equal to limit h goes to 0 of f of 1 plus h minus f of 1 divided by h, and that is limit h goes to 0, 1 over h. Now let's work out what f of 1 plus h is. So that's 3 times 1 plus h squared plus 7 times 1 plus h minus 5. And then we have to subtract f of 1. So that is 3 times 1 plus 7 times 1 minus 5. That looks complicated, but it's really not. If we work out all the terms, then we'll see that what we have in between parentheses is a quadratic expression in h. So let's figure that out. I have 1 over h. Let's collect all the terms in h squared. That's just 3 times h squared. Now the terms in h, we're going to get 2 times h times 3, 6h. And then another 7h, so plus 13 times h. And then the constant terms, a lot of the constant terms are going to cancel. In fact, if you look at it carefully, you have a minus 5 here and a plus 5 here. You have a 7 times 1 here, minus 7 times 1 here. And then you're also going to get a 3 here and minus 3 here. And in fact, all the constant terms cancel against each other. That leaves us with a nice simplification. We can divide by h in both the numerator and the denominator, and we're left with limit as h goes to 0 of 3 times h plus 13, and that is of course 13. So that gives us the derivative of the function at x is equal to 1, but later on we will see that we can do this without computing the limit explicitly by just using our rules. So later on we will do this in one step. Now let's compute another derivative. So here we're given the absolute value function and we have to compute the derivative at x is equal to a, where we leave a sort of blank. First, let's have a look at the graph of absolute value of x. So absolute value of x is a very recognizable graph that looks like a V shape. So this is the graph of y is equal to absolute value of x. And now let's just think a little bit about what the derivative could be before we calculate it. So the graph basically consists of two straight lines that are joined at the origin, where they make a right angle. And if we ask for the tangent line to this graph, then it's gonna be just whatever the slope of those lines is, plus or minus 1, except at the origin. So at the origin, if you sort of try to think like what could the tangent line be at the origin, then it's not really clear. Is it this line? Is it this line? Is it this line? Is it that line or that line? It's not really clear here what happens at the origin. What would be that tangent line? So going a bit already in the head and in the direction of the calculation that we're going to perform, we will see that the function is not differentiable at x is equal to 0. Okay, now let's do some calculations. Let's compute f prime of a. And let's first assume that a is positive. Then our derivative is limit h goes to 0 of absolute value of a plus h minus a divided by h. Now, there's a few simplifications here that we can make. So we assumed that a is positive, so absolute value of a is going to be just a. Absolute value of a positive number is just that number. What about a plus h? A is positive, h can be positive or negative, but h is very small. H will go to 0 in the limit. So a plus h, if h is sufficiently small, will also be positive, so that absolute value of a plus h is also a plus h. That then gives us that the limit becomes limit h goes to 0, a plus h minus a divided by h. We see that the a's cancel here and here. We're left with the limit of h divided by h, and that will give us plus 1. That is very conform with what we see in the graph. When a is positive, we're on the right side of the graph. There, the graph is just straight line that goes up, that has unit slope, and the tangent line then also has unit slope, slope plus 1. Okay, moving on. A less than 0, f prime of a is again limit h goes to 0, absolute value a plus h minus absolute value of a divided by h. Now things are a little bit different, but not too much. A is negative, so absolute value of a is minus a, because a is negative. And same thing for a plus h, so a is negative, h can be positive or negative, but h is very small, since we're taking the limit as h goes to 0. So for h small enough, a plus h will be negative, and the absolute value will be minus a plus h. Now, if you cancel the common terms, the a, then you are left with limit h goes to 0 of minus h divided by h, and that is minus 1. That too makes sense. So we said on the right hand side, f prime of a is plus 1, and now we see on the left hand side, f prime of a is minus 1. So you see nicely the line sloping down, tangent line, same thing. Now last, we need to check what happens when a is exactly equal to 0. So for f prime of 0, then again we're going to have to compute the limit as h goes to 0. But let's be very careful here. Let's compute first the left limit, so h goes to 0 from the negative side of 0 plus h minus absolute value of 0 divided by h. Now h goes to 0 from the negative side means h is negative, and therefore absolute value of h is minus h. So our left limit becomes limit h goes to 0 minus of minus h divided by h, and that gives us minus 1. On the other hand, if we compute the right limit, limit h goes to 0 plus, of 0 plus h minus absolute value of 0 divided by h. Now, h is definitely a positive number. Absolute value of a positive number is just that number, so it's just h. We are left with limit h divided by h as h goes to 0, and that is 1. And now note, those two limits are not the same, minus 1 and plus 1. So our two-sided limit does not exist. Hence, our derivative also does not exist. Why does it not exist? Because the right limit and the left limit give you different answers. If the limit does not exist, then that is saying that the function is not differentiable at x is equal to 0. Now, moving on, we can consider the derivative as a function. So we said the derivative at x is equal to a, but now we can see a as an argument of the derivative function. So we can let a vary. And if we let things vary, then we want to reflect the notation that as an argument. So we're going to replace a by x, just notational change, and we're going to write f prime of x to emphasize that is a function of x. So here now we have a function of x. What does that function do? For every x, it gives you the derivative at that value x. How is that derivative defined? Well, very simple, same definition as before. Limit as h goes to 0 of f of x plus h minus f of x, and all of that divided by h. We will most commonly use the notation f prime for the derivative as a function, but there are other notations as well. In particular, I point out the following notation to you: df dx or ddx of f of x. These both mean take the derivative of x of f with respect to x. If you write your graph as y is equal to f of x, then you can also write your derivative as y prime or as dy dx. These 5 notations all mean the same thing. Take the derivative of the function with respect to x. Now let's do an example of that. So here we have to show that the derivative of the square root function is 1 divided by 2 over the square root. This is also the kind of calculation that later on we will do in one step. Oops. So later this will be one step. But for now, let's use the definition and let's figure out if we can really show what that works out to be. Okay, so our derivative ddx of square root of x is limit as h goes to 0 of square root x plus h minus square root x divided by h. How are we going to compute that limit? If you just plug in h is equal to 0, you get square root x minus square root x, that's 0, divided by 0, that's an indeterminate form. Here we're going to have to do something to get rid of the indeterminate form. You see the square roots. What do you do if you have a limit with square roots that gives you an indeterminate form? You multiply by the conjugate. So square root x plus h plus square root x over the same thing. Square root x plus h, square root x. And now you work that out. Limit as h goes to 0. The numerator becomes x plus h minus x. The denominator becomes h square root x plus h plus square root of x. We get some nice cancellations happening. The x here and the x here cancel. And then you're left with h in the numerator h in the denominator, so you can divide those out, h here and h here. What are you left with? You will be left with limit h goes to 0 of 1 over square root x plus h plus square root x. Now if you let h go to 0 in that expression, you will get 1 over 2 times square root x, which is precisely what we had to show. Again, in a few minutes from now, or maybe in the next lecture, we will do this computation in one go once we have a rule for it. For now, we don't have that rule. We have our limit definition. We can always use the limit definition. Now, a little bit more terminology. We're going to say that the function f of x is differentiable on an interval, closed interval a, b, if the function has a derivative, f prime of x exists for each x in the open interval a, b. So this is for each x, so that x is strictly greater than a and strictly less than b. And at the lower bound of the interval, x is a, we want the right derivative to exist. How do you define the right derivative? F prime a, the right derivative is same definition as for the ordinary derivative, except now you take a right limit. You let h go to 0 plus. And then on the other end of the interval, x is b, the left derivative should exist. How do you find that? Well, again, same definition, but you take a left limit. This is very similar to being continuous on an interval. So here, compare with continuous on an interval. Okay. We've already now alluded at continuity. We have a new notion, differentiability. How are the two related, or are the two related a priori? It turns out yes. If your function f of x is differentiable at x is equal to a, then automatically your function will be continuous at x is equal to a. But the converse is not necessarily true. So continuous does not mean differentiability. The example here says, show that the absolute value function is differentiable for all x's different from 0. We've already done that, actually, when we computed the derivative. So, see previous. But I want to point out one thing. So, we know that f of x being the absolute value function, we've seen already before that this is continuous at x is equal to 0, but we've also seen that this is not differentiable at x is equal to 0. And you can also observe that from the graph. If we draw the graph one more time, then I can draw that graph without lifting my pencil. In particular, at the origin, at x is equal to 0, the graph is continuous. But we also see that at the origin, you can't draw a tangent line. There, the function is not differentiable. Now that we can compute the derivative of a function, we can also compute the derivative of the derivative. And we can then compute the derivative again. If we do that, we get so-called higher order derivatives. F prime we will call the first order derivative. The derivative of the first derivative we will call the second derivative. We will denote that by f double prime, and so on. So our derivative, remember, is a function of x, so we can take its derivative, and then that gives us a higher order derivative. Notation-wise, one thing to be slightly careful about is we will not keep writing primes on a function to indicate the derivative. So maybe 3 primes for the third derivative is probably the highest that we will go. And this is d dx of f double prime of x. We will, at that point, probably just start noting the derivative as f and then 3 between parentheses x. And this is especially obvious to be a good notation. For example, f7 prime of x. If we use the primes, then we would have to write f prime 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 x. This is of course something that we don't want to write, so our 7 derivative here we would definitely just write as f7. Now we're going to establish a few rules to compute derivatives of simple functions. Let's start with the simplest function that we have, the constant function. Derivative of a constant is always equal to 0. Why is that? Let's prove it. So for 1, we have limit h goes to 0. So this actually should be a bit more explicit. ddx of a constant c is limit as h goes to 0 of the function at x plus h, but it's a constant function, so that is c minus the function at x. Again, it's constant, so that's just c, and divided by h. So we have limit of 0 over h as h goes to 0, and that is just 0. Now the second rule is a little bit more complicated. If we have x to the power n and we take the derivative, then we will get n times x to the power n minus 1. Let's derive that. So ddx of x to the power n is limit as h goes to 0, x plus h to the power n minus x to the power n divided by h. And now we want to write out the x plus h to the power n. So here, this is the term that we'll have to simplify a little bit. And here I'm gonna give you something, a result that we will prove more rigorously later when we talk about the binomial expansion. X plus h to the power n is going to be the following. It's going to give us x to the power n plus h times n x to the power n minus 1. And then there's going to be a bunch more terms, but the terms that are left are going to be of the form some constant, some coefficient, h squared, x to the n minus 2, plus a whole bunch of terms, plus h to the power n. And in particular, what I want you to focus on, I'm not going to tell you what these coefficients are, that's why I just wrote a box, but in each case you have h to some power, h squared, the next term will have h to the power 3, and so on, all the way up to h to the power n. Okay, so now let's use that. We have limit as h goes to 0 of x to the power n plus h times n x to the power n minus 1 plus something something h squared x to the n minus 2 plus something something h to the power 3 xn minus 3 plus dot 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 plus last term is h to the power n and then minus x to the power n. And all of that now you have to divide by h. Now there's a whole bunch of things that are going to cancel, and then also a bunch of things that are going to go to 0. Actually, the thing that cancels is x to the power n here and x to the power n here. All right, so what does that leave us with? Now we have a bunch of terms that all have an h in it. H here, h squared, h to the power 3, all the way up to h to the power n. And we're also dividing by h. So let's remove one h And we are left with limit h goes to 0, n times x to the power n minus 1, and then some coefficient h times x to the power n minus 2, some coefficient h squared, x to the n minus 3, and then a bunch more such terms, and then the h to the power n, when you divide by h, you're left with h to the n minus 1. And now look at what happens to the limit. When we let h go to 0, the only thing that's left is this term. Here you have an h, so this term will go to 0. Here you have an h squared, so this term also will go to 0. All of these terms will go to 0. This one will also go to 0 as h goes to 0. And what are we left with? Basically only the first term. So our limit becomes n times x to the power n minus 1, just like we had to prove. And this is also why I didn't tell you what the coefficients were in the binomial expansion. We can actually write them down. We will do that in a few weeks from now. But it doesn't matter because the term that they multiply will just go to 0 when h goes to 0. Rule number 1 says if you have a constant, then the derivative of that constant is always. Okay, moving on. Some more rules that we can use to our advantage. If we take the derivative of c times a function, the c can come out of the derivative and we get c times derivative of the function. Rule number 4, derivative of f plus g, sum of two functions, is derivative of the first plus derivative of the second. We're not going to prove these. You can, if you want to, just by writing down the limit definition. We're just going to assume them as given, and I also expect you to know these rules by heart. First of all, by rule equal to 0, so, as well as the other derivatives rules that we're going to see in a moment. So here, same function again, just like we had before when we computed the derivative with the help of the limits. Now let's use the first 4 rules that we've established. So d dx of 3 times x squared plus 7x minus 5 is what? Well, 4. You can write this as d dx of 3 times x squared plus d dx of 7 times x plus d dx of minus 5. Now, here, this last term, I can say this is going to be 0 through rule number 1. What about the other terms? Well, we can take out the coefficient here and here, and we can write the derivative as the derivative as 3 times d dx of x squared plus 7 times d dx x and then plus 0. And that we were allowed to do because of rule number 3. Now we have derivative of x raised to some power, so here we can use rule number 2. You can write this as 3 times 2x plus 7 times, and then derivative of x, that is just 1. And then plus 0, just to carry it along. If we simplify, what do we have? 6 times x plus 7. And here too, if you plug in x is equal to 1, you get 13. That's the same answer as we had before. So you see already how the rules can help you compute derivatives more easily. On the exam, on the quiz, you do not have to write down every rule separately. You can combine multiple rules in one go. In particular, I expect you to be able to, after a few exercises, to compute the derivative of a polynomial in one step. Here we used 4 steps, but I would normally do this just in one step. Now, a few more simple functions that we've encountered, whose derivative we can compute. Exponential, ddx of e to the power x, that's just the exponential again. Derivative of the natural logarithm, ln of x, is 1 over x. Very important rules, so make sure you remember these off the top of your head. Now, what if we have a different base than e in our exponential or in the logarithm? Well, then the rule is almost the same. ddx of a to the power x is a to the power x times natural logarithm of a. And ddx of logarithm base a of x is 1 over x times 1 over natural logarithm of a. These two rules, the last two, are going to follow from the chain rule. So if there's time, we will briefly revisit them and derive them from the earlier rules for e to the power x and natural logarithm of x. But that is not something that we're going to do just now. Then very common confusion that you should be aware of is the rules for a to the power x and x to the power n. They are quite different. So remember this for the exam. ddx of a to the power x is a to the power x natural logarithm of a. So that is for a fixed base and a variable exponent. But for x to the power n, the derivative is n times x to the n minus 1. So this is when the base is a variable, but the exponent is fixed exponent. So you see the rules are quite different. Make sure you use the right rule in the right circumstances. About derivatives of powers, we said you have to be careful. If you have a fixed base but a variable exponent, then the rule is the first one here. But if you have a variable base and a fixed exponent, then you get another rule altogether. Now, 2 more rules, very convenient rules. What happens if you take the derivative of a product of functions, so f times g, or the derivative of f divided by g, a quotient? So this we will call the product rule or Leibniz rule, after the person that invented it. And then the second rule here, we will sometimes refer to this as the quotient rule. Now, what happens if you take derivative of f times g? You will get times g plus f times derivative of g. What if you have f divided by g? Well, you get an expression on the right hand side, derivative of f times g minus f times derivative of g divided by g squared. So let's do a couple of examples on this real quick. Here we have ddx of x squared times e to the power x. So that's ddx of x squared times e to the x plus x squared ddx of e to the power x. Now, the derivatives on the right hand side we can compute. Derivative of x squared, that is 2 times x. Derivative of e to the power x, that is e to the x. So finally, we are left with e to the x, or 2 times e to the x times x, plus x squared times e to the x. Okay, moving on to the second example, that's a rational function, quotient of 2 simple functions. What are we going to get? Well, complicated fraction, denominator or numerator is derivative of x plus 1, and that you do times x plus 3, minus x plus 1 times derivative of x plus 3, and all of that you divide by x plus 3 squared. Now if you go look at the simple derivatives here on the right hand side, d dx of x plus 1, that is just 1, and same thing for d dx of x plus 3. So if you simplify a little bit, you get x plus 3 minus x plus 1. That gives you 2, and then you have the denominator x plus 3 squared. We talked about f. What about trigonometric functions, sine, cosine, and tangent? Derivative of sine is cosine, derivative of cosine is negative sine, and derivative of tangent is 1 over cosine squared. Let's take just a minute to prove these rules. So let's start with the derivative of sine x. Let's work it out with our limit. Limit as h goes to 0 of sine x plus h minus sine x divided by h. And now we're just going to write out the sine x plus h. So this is limit h goes to 0, sine x cosine h minus, plus cosine x sine h, and then minus sine x. And all of that we divide by h. So now you have a bunch of terms that have an h in it. You have cosine h here, you have sine h here, and then you have an h here. What do you have that doesn't have a cosine or sine of h? Well, you have sine x here and here, and then you also have cosine x here. So these terms, sine x, cosine x, sine x again, they have an x in them, so they're functions of x. But they're not functions of h. And the limit computes limit as h goes to 0, so it only cares about the h. What does that mean? It means that we can take sine x, cosine x, and sine x again, and we can take that out of the limit. And if we do that, we end up with sine x times limit h goes to 0, cosine h minus 1 divided by h, and then plus cosine x limit h goes to 0, sine h over h. And here you see two very important limits showing up. These are the limits where I asked you the last time to just memorize these things. In particular, limit of sine h over h as h goes to 0, that is equal to 1. And then the other limit is equal to 0. What are you left with? You are left with cosine x. Okay, so that shows you the first rule. The second rule you can derive in pretty much the same way, so I'm not going to do that. Let's have a very quick look at the last rule, the derivative of tangent. So let's make a bit of space here. d dx of tangent of x, that's d dx of sine x divided by cosine x. So here use your quotient rule. So you're going to have sine prime of x, cosine x, minus cosine prime times sine x divided by cosine squared. Now you know derivative of sine is cosine, so the first term here becomes cosine squared x. Now derivative of cosine is negative sine, so the second term becomes sine squared plus sine squared, and you have to divide that by cosine squared. Now cosine squared plus sine squared is of course 1. We're left with 1 over cosine squared. Next up are the remaining three trigonometric functions: cosecant, secant, and cotangent. Derivative of cosecant is negative cotangent times cosecant. Derivative of secant is tan times secant. And derivative of cotangent is negative cosecant squared. You can also, of course, write these in terms of elementary sine, cosine, and tangent. So, for example, for the first one, we will have negative cosine x over sine squared of x. For the second one, we have sine, cosine, sine over cosine times another 1 over cosine. So we get sine x over cosine squared. And then for the last, cosecant is, of course, 1 over sine. So we get minus 1 over sine squared. Now, how do you derive these expressions? So I'll be honest with you, I never memorize these because I can easily rewrite them if I have to. The easiest way is to use the chain rule that we will see later on, but you can also use the quotient rule. Let's take, for example, here on the bottom of the slide, derivative of cosecant. Well, that's derivative of 1 over sine. Now, 1 divided by sine, that's a quotient of two functions, constant function 1 and function sine. You use your cotangent, your quotient rule, and you're going to get derivative of 1 times sine minus derivative of sine times 1 divided by sine squared. And then what is left to do is you basically express that derivative of 1, constant 1 is 0. Derivative of sine is cosine x. And your expression simplifies to negative cosine divided by sine squared. As mentioned on the slides and before, this derivation will be even easier once we cover the chain rule. Now, 3 more functions whose derivative we can compute: arcsine, arccosine, arctangent, and the derivative is listed here on the slide. At this point in time, it is very tempting to say, oh, when am I ever going to need the derivative of an inverse trigonometric function? Well, it turns out that these expressions are very important. In particular, the derivative of the arctangent being equal to 1 divided by 1 plus x squared. So this one right here, this is going to come back when we take integrals of rational functions. But the other two are also going to play a role. And here with these 3, I really ask you to memorize them. So know the form of these 3 functions so that you can write them down on the exam without any hesitation. These expressions will come back many, many times. Now, the last part that we have to cover is the so-called chain rule. What does the chain rule allow us to do? It allows us to take the derivative of a composite function. We've already encountered that when we talked about continuous functions and the composition, but just as a reminder, what is a composite function? Well, we write it as f after g, and f after g is itself a function of x. And how is it defined? Well, you first take g of x and then you take f of the result, so f of g of x. If f and g are differentiable, then the composite is also going to be differentiable. And we can even write down the expression for the derivative. The derivative of the composite is derivative of f evaluated at g times derivative of g evaluated at x. So this is a very specific form, and I'm going to ask you to do lots of exercises on this because this is a very important expression for composite functions. maybe a couple of examples. Let's first do a simple example. So let's say we have a composite function f of x is sine of x squared. That is a composite function. The inner function, the g, is x squared. The outer function, the f, is sine. So let's put some colors on that to make that clearer. So here your x squared, that's g of x, and your sine, that is f. Okay, now what does the chain rule tell us? F prime of x, or in other words, d dx of sine x squared is gonna be the following. Let's stick with the colors. So we have f of y is sine of y, and we're going to need the derivative of y. F prime of y, that is cosine of y. And you see here, the first thing is that f prime. So you're going to take your f prime, your cosine in this case, and you're going to put it there. Now, your cosine is not going to be a function of y or of x. You're going to evaluate it at g of x. What is g of x? G of x is x squared. So here you get cosine of x squared. And then last, you have to multiply by g prime. But that is easy. If g is x squared, then g prime is 2 times x. So here we're going to multiply by 2x. Now if I write that down one more time without colors, I get cosine x squared times 2x. With the chain rule, you can compute the derivative of arbitrarily complicated functions, as long as they're compositions of simpler functions. Here, I've written down everything with the help of colors, with a number of extra steps, but I also expect you on the exam to be able to do computation with the chain rule in one go. There will be at least one question about the chain rule on the exam and or on the quizzes, so make sure you really know this, otherwise you have an important lack in your knowledge. Back slide. In fact, let's do a couple of examples that are a little bit tougher. The first one here, the derivative of e to the power square root cosine x. I'm going to let you do that one yourself. And what we're going to, if we go, do is we're going to go straight to the derivative of x to the power sine x. So remember, we see that both the base and the exponent are variable. They are both functions of x. Base and exponent, both variable. So a priori, there's nothing that you can do, no rule to apply to this derivative. What you can do instead is you can be a little bit tricky. You can think about the fact that you have something raised to another point, to another value. So here I want to recall some algebra for you. If we have a to the power b, then we can write it in a different way. You can write this as e to the power b times logarithm of a. If you don't remember that, this is actually quite easy to see. E to the power b times logarithm. You can take the b and put it back in the logarithm. You get e to the power logarithm a to the b. And if you have e to the power logarithm of something, those two are each other's inverse functions, and you end up with just a to the b. Now, what you have on the left, a to the b, that looks simple. What you have on the right, that doesn't look so simple anymore, but it's actually going to be a simplification for us. So here, we're going to let a be x and b be sine x, and then what do we get? X to the sine x, according to this rule, is e to the sine x logarithm of x. Okay, so now we can use that to compute our derivative. d dx of e to the sine x logarithm of x. What is it? Well, chain rule. So first, let's use the colors one more time. The e to the power, that's going to be our f, our outer function. And then sine x logarithm of x is going to be our g of x, our inner function. And we use the chain rule, we get e, because derivative of e to the x is just e to the x, so we get e to the power, and then g of x, sine x logarithm of x. And now we have to multiply that by the derivative of g. For the derivative of g, it's sine times logarithm. We can use our product rule. We get cosine x logarithm of x plus sine x times 1 over x. This whole thing here is g prime of x. So now let me abandon the colors one more time. What we have, e to the sine x, ln x, and then cosine x, ln x plus sine x divided by x. And we can do one more simplification. Here up front we have this term, but we established that this term is actually just x to the power sine x. So we can write this as x to the sine x cosine x logarithm x plus sine x divided by x. Okay, what is the takeaway lesson from this? So we started with quite a complicated function, and by some algebraic rewriting we were able to compute the derivative with the help of the chain rule. It's a very common occurrence where the chain rule is really going to be the thing that allows you to compute the derivative. At this point, we are actually done with our first slide deck on derivatives. The takeaway message for the slide deck as a whole is remember the rules that we've established, because if you take them all together, they will allow you to compute the derivative of any function. No matter how complicated, you will be able to compute a derivative. Okay, there are functions whose derivative you cannot compute, that are genuinely too hard, but we'll of course not pose these on the exam. On the exam, you'll always have things that you can easily compute the derivative of, and these are then very good exercises to have a look at, because they will give you lots of marks. So with that, we conclude this video. The next lecture will conclude derivatives and will take place in class next Wednesday. Thank you.